All right, the one I want you to add to your cardstock is number 5 on that worksheet 3A. So go to number 5. You should have expanded it. It's set out to a 5th degree. Look at your number 5. Are you looking at it? And then we'll pass it up. On the cardstock, draw a little line under the last one you did. I think it was e to the x's expansion. And we're going to write out the 1 for 1 over x plus 1. It'll help us in a later. Maybe not, but kind of. So what did it start with? When you already did the work for it. What was it? It's a simple one once it cleans up. It started with a 1 and then what? Minus x. Then what did it have? X squared. And there's no, all the factorials disappeared, which makes this one a real simple looking expansion. I want you to go like that. I've been having you insert something on these ahead of their time, and it comes in today. We are going to insert what we call a formula for the nth term. So that's more in another day from now, but I've been having you practice. This has an alternator in it, so there's a -1, right? There's no factorial in it. It's just -1 to some power, and then it's x to a power. I would like it to be x to the n. Are you okay with that? The problem is then what must my counting mechanism start at? 0. So I'll write down here that n is greater than or equal to 0. Is that then okay for me to put a little n on here? Or do I need to tweak it? And you just run it through. If it's 0, will it generate a positive? That it's fine as it is. All right, that's called the nth term. We're later going to call that a general term. Then what I want you to do is write it as a series. So go dot, dot, dot. That will continue to infinity. We're going to write it as a summation. This is actually the sum as n goes from 0 to infinity. That's where I'm going to start my count. Watch your count starts. They either all start at 0 or 1. You just need to try 1. If that doesn't work, put in the other one. -1 to the n, x to the n. All right, that's all I need you to add to that cardstock right now, and that's all I need from 3A. At the top of your notes, a power series. This is a new word for you. We've been working with series, but I've never had the word power in front of it. And you'll notice what's different from what you did on your last test is the introduction of this variable x in it. Ours all only had n's in them, like we did the harmonic, which was the sum for n goes from 1 to infinity, 1 over n. And we did the n factorial over 2 to the n. And we did n squared plus 6n plus 9 over 4n. They all only had n's in them. A power series is a function of x. So that's new and that's new. I'll have you write those both down. The a sub n, they're really polynomials if you were to write these out. They're polynomials of degree x. This a sub n generates the coefficients of the polynomials. Generates coefficients. All right. The n can start at 0 or 1. That's loose. It depends on the problem. But you'll notice they have an x in them. That's new. These are functions. Different numbers go in for x. I could do it 1 or 2 or 3 or 4. All right. So when you talk about functions, you talk about their domains. For a power series, the domain is all x values for which the series converges. This is going to be really confusing for a while until we go do an example. But before we do one, I'm going to show you a graphical interpretation with that one we just wrote out. So I'm going to take you don't need to take your calculator out. I've got mine. I'll go back a page to that number 5 that we wrote out before we called it a power series. Where did I put it? Am I a page off? This one right here. This is called the power series for this function. Just a second. Hold up. Don't ask me any questions yet. It's going to take it. I'll cover them all, I swear. For a while, I just need to talk and show you a graph. So this right here is called a power series. It's for this function. The domain for this series is all x values that make this converge, which means it matches up exactly with the graph. When we did the one for sine and we first started, do you remember how I kept upping the degree and you would see it wrap around the polynomial better and better and better? The one for sine actually converges for all x, which means when you go to the infinities, it's a dead ringer. It converges everywhere. This one does not, and I'm going to show you on the graphing calculator. Just it helps if you get a visual before I give you all the steps. Super important. So calculator. I'll have the function itself graphed. Historically, they couldn't graph the function itself. Well, they could guesstimate, I guess. Where's my graphing calculator? There it is. All right. So you'll see, you don't need to take yours out. There's the function, right? I made a power series for it. I obviously can't go to infinity here, but we did it out to the fifth, right? So I'll start that. It was 1, and then you guys said it was minus x, you created it, plus x squared. If I were just to hit graph right now, I'll have a parabola on this curve. You all right with that? Watch. Graph. Is that a dead ringer everywhere? Totally not. It's got huge issues over to the right of 1, right? In here it looks pretty good, and then it's pretty bad to the left of -1 also. I can make it better. But do you see how I'm never going to be able to deal with this left-hand lobe? Because my polynomial can't hop an asymptote, right? So for sure, I'm not going to have convergence to the left of -1 ever. I can make it fit that a little better, so I'll do that. To make it fit a little better, what will I just do? Yeah, let's go out to the fifth that you had to do. We'll go, and again, it's an approximation until I go out to infinity. And then I have to talk about what x values is it perfect for. And on this one, there is a restriction. It won't be a perfect fit everywhere, but it'll do an okay job in a certain region of the graph. And we'll guess at that region. Oh, dang it. Sorry, I'm trying to talk and type at the same time. X to the fourth, and we went out to the fifth, right? Minus x to the fifth. All right, so this is my Maclaurin polynomial graph that's approximating the behavior of the curve. It's horrible in the negative region. It's pretty good in here. Can you guess at what it's pretty good from? Probably from where to where? -1 out to 1. And when we do our work today, that's what we're going to be calling the interval of convergence. -1 to 1. We're going to find it without graphing and guessing. But what that means is in the region from -1 to 1, those are a really good match. They're actually perfect if I were to take that out to infinity, but this is never going to correct itself, and that's never going to get hit over there. The sine, cosine, and e to the x, guess what their domains are? All real numbers, and that'll fall out mathematically. They're dead ringers, which is why they can be programmed into our calculators so nicely. They work for all x, so you can do the sine of 11 and it's fine with it. This polynomial for this function's only good in a small window. We're going to be calling this, go ahead and look up at the screen. That right there is going to be called the center. The amount out you can go from the center, we're going to call the radius. So if you look at your worksheet, there's 3 things it asks for, and I have to teach you how to find 3 things. Ask for a center. What else does 3b ask for? Radius. What else does it ask for? Interval of convergence. So I wanted to show you graphically before I tell you how to find them with the math, just so the math isn't going to be that bad, but you'll forget it if you don't understand the graphical significance of it. So let's go back here. So it's taking a while. It's a smart board, but I'm making it do lots of stuff. All right, so all power series converge at the center. All right, so that no matter what one you make, they match up at the center for sure. After that, there's 3 things that could happen for convergence. They might converge. Let's do this. They may, actually that should say might instead of may. That's the wrong word. I allow them to converge. This should say they might. They might converge only at C. And again, you're going to know what C is based on what I've told you already. If you only see an x in your polynomial expansion, C is 0. If you see an x minus 1, what's C? 1. All right, so you'll know the center. They might converge only at C. Graphically, and you don't need to put this in your notes, but graphically that means you have some function and you fit some polynomial to it, and it really only matched up there. It's a pretty worthless scenario, and it's not going to happen mathematically for us because that's worthless. But can you give me a type that does only hit at C that we've done? The tangent lines would have been this situation, but we're out of Calc 1 now, so we're going to, our intent is to not have this happen. So I'm going to say that won't happen. However, if I had to discuss what's the radius of convergence, I would say it's 0. I can't stray anywhere from the center. If I were to talk about what we call the interval of convergence, I'm going to call it the IOC. I don't have an interval. I only have one point, so it would just have C in it. So this situation, this is what we're trying not to have happen. The other two situations, in order of least important to most, would be that they converge, but only on a certain finite, let's do that, finite interval. All right, that's what that example I just had did. It was fine on a given window. And sometimes that's the best you can do. So that will happen for you. For College Board on the AP test, that's usually what happens is they give you one that's not a dead ringer everywhere because they want you to find the interval and they want you to find the radius and they don't want it to be 0 or infinity. So usually this is the AP test. It's not the best case scenario, but that's probably what you're going to have. I'll go redraw that one that we had. It had an asymptote, the original function. It went like this, and then the polynomial I fit to it was really good, and then it went awry at 1. All right, so that would be that scenario where it's converging, but only on a certain finite interval. What is that interval? This is what we're going to call it. We're going to have an interval. This is called the center. You'll know what that is. This, what did I say we're going to call the distance you stray away from the center? The radius. So if I were to write that as an interval, I'd go the center up the radius and the center down the radius. Here's the thing that's going to be a little bit tricky, is what happens at the endpoints of the interval varies from problem to problem. You have to test to see whether you do beefies or wimpies. That's got to be a test. So right now, I'm going to put a little set of wimpies in here because that's a decision you're going to need to make, beefy or wimpy brackets. I'll teach you how to do that. Third case scenario, what do you anticipate I'm going to write? Converges where? Everywhere. That's the best case scenario. It means you've got a polynomial that wraps the function completely, solidly out to the infinities, and it can be used in any kind of computer programming or math that you want to use it for. You can do derivatives, integrals, add, subtract, multiply, divide, and it will have the exact same behavior as the function itself. So this is what we really like to have happen. This is what's probably going to have happen. All right, so let's write this. It converges for all x element of the real numbers. That's what that means. It means for every single number, it means it's a dead ringer. Now anticipate, what do you think we'd call the radius in this scenario then? What do you think? How far could I stray from the center and have it be a ringer? Infinity. Yeah, so when that happens, we're going to say the radius is infinity, and we're going to say the interval of convergence is everywhere. So we're going to write that like this, and that you should never put beefy brackets on infinities, so we're going to leave those open. All right, so how do I figure this out? Because I can't get the interval until I can get that radius of convergence, and we can't graph them. We're going to even pretend we don't even have AAA batteries, let alone a graphing calculator. So how do you decide this? It's one of those tests back there. The best test and the most applicable is going to be the ratio test. All right, that's going to be the one we use 80% of the time. So we need to, that's why I've been trying to get you to hold that one solid for a long time. When you run a ratio test, you take a limit, right? As n approaches infinity, we've been stressing absolute value. It's super important with these. We do the next one divided by the one we have. And for convergence, what has to happen with that limit? So we're going to find all, do you anticipate what we're going to do? We're going to find all the values of x that forces this limit to be less than 1. That'll give us where we can be. All right? Ratio test is great. I'm going to put a star by that one. On that worksheet, I think you're going to use the ratio test. I think there 6 or 8 problems on there. 8 total, 4 in the front. I bet 6 of the 8, if not 7 of the 8, you're just going to do the ratio test. It works for all of them. So you can just say, I'm only going to do the ratio test. However, the root test can work too. The root test, you have to be able to write it as the limit as n approaches infinity. And remember, that's got to be the nth root of, again, absolute value to the nth power. But we still need to force that to be less than 1 for convergence, because we're only looking, we're going to be doing intervals of convergence. Where do these functions and their power series equal each other or converge? The last one is if there's a geometric series. Okay? If you happen to have a geometric series, when does it converge? Yeah, the absolute value of your common ratio is less than 1. This is easy to spot, easy to run, easy to interpret. It only happens every once in a while, but it's kind of nice. Plus for geometric, I'll tell you what also happens. When you have a geometric series, it's always wimpy. Okay? I'll prove it. I'll show you why, but intuitively it kind of makes sense that you can't have your common ratio be a 1. Right? That would be, nothing would grow, or that's exponential growth and decay, and that doesn't cause a change. All right, so once we have the interval of convergence, if it's finite, like you don't get from negative infinity to infinity, but you decide that, okay, I know my interval is between -2 and 2 that I have convergence. You have to decide whether you do 2 beefies, 2 wimpies, or 1 of each. All right? That means you have to test the endpoints. You actually need to physically go plug these in and see what happens. And until I do one, you won't get that. But just bear with me. There are the tests in hierarchy of what you're going to run. A lot of these series are going to be alternating. So if you can run an alternating series test on it, that would be awesome. When does an alternating series test converge? When in the absence of the alternator, the rule of sequence does. So you should know that. The other one that you're going to be using a lot are the harmonics. And you might say, we only know one harmonic. You know the divergent harmonic. But there's actually, here's the divergent harmonic, right? And goes from 1 to infinity. That's the divergent harmonic. But all variations of that, I could do A, N plus B. Those are all called harmonics, and they all also diverge. Can you tell me what test could easily prove that all things of this form must diverge? The LCT. Compare it with this guy, right? With the LCT, divide it, you get an N on the top. Take its limit, which is 1 over A, finite and positive. You don't need to repeat all that anymore. You can just say this is a divergent harmonic. In this test, that you don't need to go into all the detail. The other one, this is the big one. This is almost as big of a star. The other one is every once in a while there's a P series that pops out. Not too often, but remember what that one says. 1 over the N to the P converges, and I should put my counting mechanism on here, converges when what happens?
P is greater.
Converge when P is greater than 1. All right, so I haven't done an example yet. I'm getting there. They don't take me very long. Now this is like your homework. So I'm digging right in here. For each power series, remember what distinguishes a power series from just the series we've been doing? They're functions. Yeah, there's an X in there as well as N's. Identify the center. Let's go do that right now. The center for most of them is 0. Let's write it off to the side. We're going to fill in the center, the radius of convergence, and the interval of convergence by the time we're done with all of these. What's the center on number 1? 0. Okay. What's the center for number 2? Center for number 2. No. 0. It's not x minus 1. It's not x minus 2. It's just x. That one's got a center of 0. Let's do radius IOC. Flip it over. Let's just pick those centers off. That's an easy question. This one's center is also 0. I'll find a radius. I'll find where there's convergence. And then the last one, what's its center? -1. That was actually to the center on the example I graphed. It had an x plus 1 in the denominator, right? So this is an r that I'm going to find and an interval of convergence that I'm going to find. I'm going to start with actually the wimpiest kind. They're kind of annoying because they're common sense and you have to show some work. But watch, this is no longer 1/7 to the n. If it were, that's a numerical series. Does it converge or diverge if that was 1/7? Converge. So 1 is in my domain, right? It's obvious. Would 2 be in my domain? Yes. 3? Yes. -2? Yes. Everything between what and what? -7 and 7, but you have to show that. Yes.
So it's all integer values of x?
Mm-hmm. Yeah. Well, no. No.
So it could be like 1,
Yes, it's anything in between them because we're thinking graphically. Good question, and I answered it too quickly. Actually, you could use ratio, you could use root, or this one's geometric. Ratio works on all of them. The other two are quicker when they work. Which one's the easiest one on this one? Yeah, just go like this. The absolute value of x over 7 to force convergence, because that's what we're looking for. How far out do we need to go from the center to converge? And then let's write that as an interval. That would have to be less than 1 to force convergence. 7 is always 7 in absolute value, so you could go like that. That means the absolute value of x would have to be less than 1. Right now, 7. Right now, this is called the radius. It's how far I can stray from the center, which is 0, left or right, to have convergence. This one's so simple. They aren't all like that. I would go over here and say I've got a radius of 7. I can go 7 to the right of 0 and 7 to the left of 0, and all numbers in here, that series will converge. For all others, it will diverge. All right? So down here, I have what I'd call an interval of convergence. I would say x has got to be less than 7, greater than -7. And I would go like this. But what did I tell you? You also have to discern whether the 7s work. And when it's geometric, it's obvious that they don't. You're always going to exclude them, but let me show you why. And let me show you how many points that's worth on the AP test. Because here's one we'll do this one later. But if you take a look, it says considers both endpoints with analysis and the proper interval. So you do have to verify that. You can't just, even if it is common sense, I can get, for the AP it won't be, just so they can avoid not having to grade kids who say it's just common sense. Let me show you how you do that. You need to test the endpoint. So I'm going to say test x equals 7. Okay, that's this endpoint. I'm going to test it. Where am I going to test it? Right there. I'm going to do a specific case of the endpoint going into the domain. What would that give me? The sum of n equals 0 to infinity of 1 to the n, which is 1 plus 1 plus 1 plus 1, which so totally does what? Diverges. And you can just say which diverges. I guess if you had to say a test, you could say the nth term test, because that limit certainly isn't going to be 0, right? So you could say diverges by the nth term test, but that's obvious. Likewise, if you were to test -7 in the domain of your power series, I feel like you're getting it. You're quiet, but I think you're quietly really listening, so I'm feeling good about it. If you were to picture writing that out, it'd go 1 plus -1 plus 1 plus -1. What did we call that? Diverges by oscillation. But you can just write which diverges. It's so obvious, and honestly, testing-wise, you won't have this scenario because it is too obvious. You could avoid everything I'm going to teach you just by common sense. The ratio's got to be between -1 and 1. So that one's too obvious. Let's go to a new one. All right. So center's still 0 because it's just x. The only test I can launch on this one is which one? Ratio. This is how the ratio test works. I take the limit as n approaches infinity of x to the n plus 1. So I replace, remember we've done this, right? All over n plus 1. And then I divide it, also known as multiply by a reciprocal, by the original. This is locked into absolute values, and I'm looking for x's that'll force what? Convergence. Are you with me so far? It looks way harder than it is if you get what's going on. Then you're going to clean up in here just like we always do with our ratio test. The x to the n plus 1 is really x to the nth times n. It's going to cancel. It's going to leave an x on the top. Are you all right with that? Okay. And then I have an n and an n plus 1. I'm going to wait for you to catch up. In this scenario, x's are numbers that are going into this function. It could be a 2 or a 3 or a 4 or a 5, but it's a constant in every scenario. Like when I say f of x and I say x is 7. 7's a constant. So regardless of what happens, constants come out front of limits, derivatives, and integrals. Wouldn't you agree? So you're going to take all non-counting mechanism terms. What I mean by that's all things without n's in them. But mathematically, it's because this is a function. These are numbers going into a function. You get to pull it out front, just like we always do. It's the absolute value of it still. That's important. But now we're just taking a limit as n approaches infinity of an expression involving only n's. Let's talk about that. Are you ready? What's the limit as n approaches infinity of n over n plus 1? 1. You don't need to prove why. You don't need a L'Hopital. At this level, it's assumed. So that you can just, that goes to 1. All right. What does that leave me with? The absolute value of x has to be less than 1. What did I say we call that 1? The radius. Yes. What that means is I can stray 1 to the right or 1 to the left of 0, and I'm entirely confident I have convergence between the function and whatever power this power series representing it. You might say, what's the original function? At this point, I don't know for that one. Okay, I don't know. But if it were representing it, I would have convergence from -1 to 1. So here's your interval of convergence. We call it the IOC. -1 to 1, but I'm not quite sure whether I'm beefy or whether I'm wimpy. Could be both, could be one of each. How did I tell you to decide? That's the next step, and it matters. They change all the time from problem to problem, okay? How did I tell you to see? Plug it back in. To what? X. Into the summation. Yeah, go back to your power series up here, okay? And we're going to test. I like to test the left one first just to keep myself organized. On the last one, I actually didn't. I like to be consistent. So I'm going to test x equals -1. That means I'm going to put it into the domain of my series function, also known as a power series, and I'll be taking the limit as n goes from 1 to infinity of -1 to the nth over n. I told you, you got to hold all that stuff up. Because that, you have to decide whether it converges or diverges and state why. Because it's a 50-50 guess. That converges by the what? AST. That's all you need to put for these. You don't have to say, because the limit without the alternator goes to 0, therefore by the 8. You can just go like this. -1 to the n over n converges by the AST. So now let's go put our interval of convergence. -1 gets to be included in my domain. Now watch me test 1. See, this is actually kind of important, and it's something I think gets skipped or people don't get why it's working. So let's go do that. Now let's test the other endpoint on the interval of convergence and see if it truly causes convergence or divergence. Can I include it or not? Back up to here, when I replace that with a 1, I'm going to get 1 over n. Because it's 1 to the nth over n. What's that? Divergent what? So you can just write the divergent harmonic. Or you could write a divergent harmonic. But diverges, maybe put in parentheses, harmonic. Because you do have to state why you know, but you don't have to be as specific as we were last chapter. You're now done. Your interval of convergence looks like that. What does this mean graphically? if you were to take a function, use Maclaurin or Taylor polynomial to expand it all out like you did on your worksheet, right? And you got this. You're 100% sure this fits your function perfectly in that interval. What do you think? Are we good? Let's go do 2 more and then we'll be done. All right. Again, this is the grading. We're going to go right to this one. Let's go a little faster. I'm going to begin. Which test? Ratio. Watch me start it. Limit. As n approaches infinity of, go to the next count. Divide it by, also known as multiply by the reciprocal, the original. Make sure you do absolute value, and we're forcing convergence. That's not memorizing a thing, right? Because it calls, did I forget something? Did I not flip it? Oh, you're so right. I said flip it. Thank you. Oh, thank you, Mr. Hansen. There we go. I'm going to clean that up as we always have. We do recursive for factorial, so we call this n plus 1 times what? N factorial. You can even consider this x to the nth times x if your brain likes that. Okay, we'll go cancel. You can think it, you can write it. You don't really get points for that. Just simplify it properly. So what's going to be left on the top? X. Okay. What's going to be left on the bottom? Because the x to the nth is going to go. The n factorials are going to go. This is going to leave an n plus 1. I'm finding the x's that'll force convergence. What did I say to do at this juncture? Because you get it, not because you're memorizing it. X comes out front. It's a constant. It's something going, it's a number going into a function. But yeah, Tyler, it needs to remain in its absolute value. That's super important. That's what gives you the interval. Up from the center and down from the center. I'm going to still take the limit in the absence of my x term. So that's just 1 over n plus 1. I have to force that to be less than 1. What is this limit? 0. So I'm really asking you, absolute value of x times 0 is less than 1. For what values of x? All. So you're going to say this, for all x elements of the reals. Although that won't get you points. Your points will be for giving me the radius of convergence. What is it? Infinity. Those are historically what they loved because it means, oh my goodness, we found a dead ringer for this function that's a polynomial. And polynomials are sweet to work with. So we'll talk about what this one is in just a second. Interval of convergence, no need to test my endpoints because I can't be infinity. Watch me write this function out. I'm going to change this to a 0 just so to change. It won't change my process here at all. Watch if I wrote that out. I'd have x to the 0 over 0 factorial plus x to the first plus x squared. Does this look familiar? It should. Who is this? That's E. This is E's dead ringing power series, and it wraps E perfectly, which is probably what's programmed in your calculator. That's historically, this was huge in math history. Huge. But now that we have AAA batteries and we have graphing calculators, it's not as big of a deal, right? Last one up. Are you ready? Let's begin. My radius is my center is -1 because I'm doing x minus -1. It's always x minus the center. So I'm centered, basically graphically I've got a little asymptote probably, but let's go work it on out. I'm going to take the limit. As n approaches infinity, I've got an alternating power series. I'm going to use the ratio test, and what do you think the absolute value does to the alternator? Takes it out. It kills it. So you don't even need to put it in there. You might want to write absolute value kills the alternator. That could be a t-shirt. Okay. Only we would know what it means. But yeah, so all I need to do is focus on, you could put it in there, but the absolute values are going to annihilate it anyway. So let's go like that. That's my ratio test with the n plus first term. I divide it, also known as multiply by the reciprocal. X plus 1 to the n. I'm going to force convergence. How are we doing? This is a huge section. Are we good? This is high-powered math we got going here. It's good stuff, though. Now I'm going to clean things up. So I have x plus 1 to the nth times x plus 1. So I'm going to cancel, leaving one of those up on the top. On the bottom, what's going to be left? A 2. The 2 to the n will cancel the 2 to the n, leaving 1, 2. So let's take my limit as n approaches infinity, absolute value, x plus 1 over what? 2, right? Has to be what? Less than 1. Now, if you look at it, I lost my counting mechanism, correct? Do you agree? But what did I tell you about all non-counting mechanism stuff? It comes out front. This is the absolute value of x plus 1 over 2, and 2 is 2 regardless. And really what's in here is a 1. What's the limit of 1? 1. So really, this is what I need to force to be less than 1. I can do that, right? I'll double both sides. And now I've got an inequality from Algebra 1 that needs to be solved, correct? I will have x plus 1 has to be less than 2, while at the same time greater than what? Negative 2. Or if you think of the center as being negative 1, that's actually easier and deeper thought. If your center is negative 1 and your radius is 2, it means you can go 2 to the right or left of negative 1. That would put you at negative 3 or at what? 1. I like the radius from the center, but most kids, that's too deep. They want to do a little algebra 1 in here to be safe. So here's my interval of convergence. Negative 3 to 1. Not quite sure what happens at the end point, so we beefy wimpy it. And then what do I do to decide beefies, wimpies? I plug in. All right, I test. I'm going to test negative 3. And just to make sure you get it, what am I testing it in? I'm seeing if it's in the domain of my original power series function. So it's going to go right here. And if it causes convergence, I get to include it. Let's go put our radius on here, by the way. That was 2. I can stray 2 away from the center. That's what this is saying. This is really x minus negative 1. So if you look at it as center, stray from center, you get those same endpoints. That's actually a pretty important thought. Do you get what I just said? Are we all right with that? All right. Most kids, like I say, previous years, they solve by Algebra 1 inequality instead. They don't like to think of it like that. All right, let's go test negative 3. I'll go put it in. I'm going to take a sum as n goes from 0 to infinity. I'll do negative 1 to the nth. And then when I put in a negative 3, what do I get? Negative 2 to the nth over 2 to the n. Now, how do you combat that? You've got several ways you can do it. What do you think? It's just 2 to the n on the top. Yeah, that's how powers work. You can bring them in. Like you can say 2 times 4 to the third is 2 to the third times 4 to the third, or you can call it 8 to the third. That's how they work, correct? So on the top is really just a positive 2 to the n. What is this? 1. What's the sum as n goes from 0 to infinity of 1?
Diverges.
It diverges. Yeah, it's 1 plus 1 plus 1 plus 1. It diverges by the nth term test, I guess. Its limit's 1, right? So you would write diverges. What does that mean? You better wimpy over here. And I'm going to stop because I think you get the idea, right? So we'll just stop. I'm going to hit done. You're going to start that worksheet.